Okay, so okay, so so I just wanted to give you an update what we're doing. So we will have midterm two. So on I guess it's on uh, April 30th, so 2 weeks from today. Yeah, so we will have our midterm 2 weeks from today, and the idea would be I'll send you the midterm, and then you'll have to do it, and I'll have to watch you somehow. You turn your cameras and stuff like that, and we'll have a time limit for that. Um, I will I'll probably make it shorter and less problems than midterm one. So I don't know what we will have the details later. So we will cover much less, of course, than what we were planning to. So we will the midterm will cover whatever we covered until now, plus one or two sections next, whatever we cover next week. And then we'll have a review session on Tuesday, that's April 28th, I believe, and the midterm on Thursday, which is April 30th. Okay? Any questions related to the midterm? No questions? Can you guys hear me? Yes, yes, yes. Okay. Okay, so um okay, so let's start let's continue with section 4.1. Can you see also what I'm showing to you? Because I can't see if you're seeing or not. Yes, okay. So I realized last time I was doing this thing, and then on the video this looked really small. Are you able to see it well enough? Is it big enough? Yes, okay. So today we're going to continue with section 4.2. And so last time we talked about finding the intervals where the function was increasing or decreasing. So let me just remind you of things. So last uh, time we talked about the intervals where the function increases and decreases. So f is increasing in the interval AB if the derivative is positive, and f is decreasing if f prime is negative, right, in that interval. So okay, so that's what we did last time, and then we did several examples trying to find out where the function is increasing and decreasing. So the idea was, the key point was to find the critical point. So the steps were, step 1 was find f prime x. Step 2 to find these intervals was to find where, or let's just say not find, but solve the f prime x equals to 0. And then step 3, so let's say here, and obtain intervals where the function is increasing or decreasing. And step 3 was peak points in these intervals to find out the sign of the derivative. Okay, so in each intervals, so you just do what one point. So if it's positive at that point, that means the function is increasing in the whole interval. If it's negative, it means it's decreasing in the whole interval. So let me just emphasize, as usual, f is increasing, that means derivative is positive. F is decreasing, it means that the derivative is negative. Okay, so today we're going to continue this thing and we're going to apply the derivative to finding out where the function has a maximum or a minimum. So for that, we're going to start by writing down the definitions of what means to be a maximum or a minimum. Okay, so we say that f has a global maximum at x naught if we have this inequality f at x naught, the value of the function at that particular point is greater than or equal than fx for any other x, any x in the domain. Um, so for in the domain of f. Okay, so what does that mean? That means, so you find the point, so this is this x naught, right? So f has a global maximum at that point. That means this inequality is satisfied, and that means that at that particular point in the on the real line, you have the highest point, highest corresponding point on the graph. So picture would look like this. So you have, so that's your coordinates, and you want to have somehow a graph, maybe which looks like that. And actually, I'm gonna erase this part here, right? So that's your graph, and you want to find. So on this graph, this is your y equals fx. This is x. This is y. And you want to find the highest point on the graph. So in this case, it's going to be this point here. So that's the highest point. So you have the corresponding point x naught, right? So we have, this is my x naught. So then this one would be my global maximum. Okay, so global maximum, it means that if you pick any other point on x, like this one here, then the value of the function here is smaller than at x naught. So this is basically saying that this height here is greater than that height there. Okay, so that's what that means. So global maximum, it means that the highest point of the function, and in other words, it means that the value of the function is greater at x naught than at any other point. So we say that global maximum at x naught. Okay, at x naught. So similarly, we have that f has a global minimum. So f has a global minimum at the point x naught if we have the opposite inequality. We have that f of x naught is less than or equal than fx for any x in the domain of f. Okay, so let's compare. So I have here global maximum if fx naught is greater than fx at any point, and it has a global minimum at x naught if the opposite inequality. So that's the smallest point. So let's do an example of that, the graph of that as well. So if I draw this graph here, yeah, so and so similarly, okay, so here I have that graph, and that's the graph of my y equals fx again. So this is my x, this is my y. And so where is my lowest point here? Well, here, this one here. In fact, there is 2 points here which are basically the same. I mean, no one says that the global minimum has to be 1 point. It could be several points where you have the lowest thing. So so in both of these cases, we have that this could be my x naught. Okay, so most of examples we will consider there will be just one global minimum, or one global maximum. So this is so we say that this one here is the global minimum. Okay, so that's the picture. Okay, so so that's global maximum and global minimum. So the absolute highest point and the absolute lowest point you can have. Okay, now, but there's all the other things in between which look kind of important. So let's look at any of these graphs. Let's say this one here. Well, there are all these other points, like this point here, this point here, this point here. Something happens at those points, right? So those points they're not absolute biggest points or the absolute lowest points, but they are locally, meaning in their neighborhood, in the close distance, they are the highest. So for instance, here, this point here is what we will call a local maximum. What does that mean, a local maximum? It means that if, so let's say my x is this point here, and then the value there is that number. And if I move a little bit, not too far, then my function is smaller, right? So than at that particular point. So this one here is the highest point when x is not too far from that particular point. And that's called the local maximum. Just to think of an example, think of the highest points on land, like overall on the earth, the highest point is the Everest, highest mountain is the Everest, and that's like somewhere in Asia, right? But so that would be an example of something that's absolute or global maximum. Well, what about a global maximum, say in United States? Well, since that Everest is not in United States, that's not a local maximum for United States. For United States, that would be the highest point in United States, which is, I guess, Mount McKinley, right? So so those are some examples. So let me give you the definition here. So instead of, let me actually change this definition a little bit. So here is my definition of global maximum, and I'm going to write instead instead of global, I'm gonna change this to local maximum. So what if I have a local maximum? Right? Well, it would be, the whole thing would be the same, but then all I would have to change is this. I wouldn't say for any x in the domain of f, but I would say for any x, uh, let's just say, oops, any x near x naught. Okay? So that means on this graph here, this thing here and this point here, this is a local maximum. Why is that a local maximum? Because if I'm not too far from that point, right, if I don't move too far, then that's the highest point in that neighborhood. So, right, so if I don't move too far, so it's like a mountain top, but it's not the absolute highest mountain everywhere. You have to go pretty far though to get to a higher point, right? So here it's not a global maximum because this one here is bigger, but it is a local maximum because if you stay nearby, right, in this neighborhood, it is still biggest. Similarly, we can have a local minimum, right? So local minimum, let's look at this graph here again. So I have now this point here, right? It's a local minimum. Why is it a local minimum? Because the local maximum is the second highest. That's the question. Doesn't have to be the second. It could be third or fifth or whatever. So here, let me take this example here. See, this one here, this looks like it's the highest point in this neighborhood, right? But it's not even second or third, it's actually fourth. See, this one's the highest, then there is this one here, which is higher. So this one's higher than that one, higher than that one, higher than that one.
How do you determine the neighborhood?
It just a small neighborhood. You don't have to worry about how big it is, but as long as it's kind of it looks like this, it's going to, there is some neighborhood, you don't know, it could be very tiny.
Okay.
And we'll figure out how we determine whether it's a local maximum or minimum in a little bit. But similarly here, see, at this point here we have a local minimum, but it's not the global minimum because there is a minimum which is actually smaller than this one. Okay, so those are local minima. So on this graph, all the local minima are let me just draw all the possible local minima here. So this one, local minima, are all these points. This point here, this point here, this point here, right? This one here, and also this one here. So all of them are local minima, right? Because locally they are kind of the values. And here the local maxima, so let me just write it here. So what are the local maxima? Well, that's this point here, this point here, this point here, and this point here. So there's all these local maxima and local minima. Okay. So I didn't write here the definition of local minima, but I explained it that it's the same as before. So we have a global minimum if you have this inequality here. And the only difference, if I wrote a local minimum instead of global one, then I would say just like above, x is near f, not just any x, but not any x, but near x. Okay. So, okay, so this is nice and good, and it's clear that this is an important concept. Why is it important? For instance, in economics, well, in economics, you want to maximize and minimize profit. If profit is given by some sort of a function, how do you figure out where is the maximum of that function or a minimum of the function? So there is a question here. So everything on the graph, okay, Mohammed, you have a question or you just
I
forgot to
didn't know
tune?
my mic was on. My fault.
Okay. So everything on the graph is local, but only the highest one is global. That's right. So if you're talking about maximum, yes. So there is many local maxima, but only one global maximum in this picture here, right? And similarly, in this other picture, we have many local minima, but only one, and actually two of them are global minima. So it doesn't have to be just one, right? These are the same. Okay. So now let's look at these pictures one more time and try to figure out how we can find out if we didn't know what the graph is just from the formula, okay? Whether a point is a maximum or minimum. And there is one thing which we can note immediately, and that's that so let's do this green. So let's look at the tangent lines at these points, which are local maximum and minimum. Actually, let me do it on a new page. Okay, so let's take a graph. Okay, and so right, so that's a graph. um, I'm gonna draw this a little different. Okay, so that's my graph of y equals fx. And so what are my local maxima and minima? Well, let's mark them. Those are these points here. I have a local maximum, local minimum, local max, mean, etc. Okay, so and there is just one global maximum, this point, and one global minimum, that's that point. Okay, so now let's look at the tangent lines at those points. Okay, so the tangent line at any of these points is, well, here is one. There is a tangent line there, tangent line there, 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 and there. What's common about all of this? One thing is common. At a maximum or a minimum, local maximum or a minimum, we have that the tangent line is horizontal, right? So what that tells us about the derivative, that means the derivative at that point has to be 0. So what does that tell us? If we have, if f has a local maximum or minimum at x naught, then f prime at x naught is equal to 0. Okay, so so that's what we have. So at the point where we have a local maximum or a local minimum, we have that the derivative is 0. So so we call these points where the derivative is 0 critical points. So the critical points are the points where the derivative is 0. So let me actually say here. So what are critical points? So critical points, these are the points uh, where f prime is equal to 0 or it doesn't exist, does not exist. Okay, so what's an example of something where the derivative does not exist? Well, so here is a so here so here's an example where the derivative does not exist. Okay, so see what happens at that point there. At this point here, there is no tangent line. I don't think that's the. Okay, so there is at this point here the tangent line. There is no single tangent line because from the right it's supposed to be, the slope is supposed to be that, and from the left it's supposed to be that. So see, because there is this kind of a corner, that means there is no derivative at that point, but still there is a minimum, right? So that's why we also look at the points where the function does, the derivative does not exist. So those are the critical points. Now, so the points where the derivative doesn't exist, or is it's equal to 0. So those are the critical points. In most examples, we will look at the derivative exists everywhere. So all you have to figure out or worry about is to find where the derivative is 0. But on some examples, you also have to do the points where the derivative does not exist. So so again, so if we want to find the local maxima or minima, then we have to find the places where the derivative is equal to 0. So first, find the critical points. Now then, let's look at what happens to the derivative on the right or on the left. So there is actually a test which helps you find out whether the critical point is a local maximum or a local minimum. And that's called the first derivative test. So the first derivative test. Okay, so what does this test tell you? How can we find if a critical point is a maximum or a minimum? So let's look at the picture so that we can understand. So here's a picture. So let's draw a picture of a maximum, right? So here is an example of something, right? So we have a maximum at this point here, okay? So what can we say about the derivative? So at this particular point, at point x naught, the derivative is 0 because the tangent is horizontal. Now let's take a point which is to the left of x naught. So let's take any point there. So let's take this point here, x. So what can I say about the derivative at that point? Well, let's look. At that point, the derivative is the slope of the tangent line, and the tangent line looks like this. So what does that mean? It means that the derivative at that point, f prime at x, is positive, right? That's what that means from the picture. Now, if I take another point here, let's take this point here, right? Let's call this my y, or yeah, let's call it, that's not y, let's call it also x. So at that point here, I have f prime at x is negative, right? Because the slope looks like this, right? The tangent line is that one there, okay? So we have the derivative is less. So again, so that, what does this mean? That means that to the left of x naught, my derivative is going to be positive. And to the right of x naught, the derivative is going to be negative. So that's basically saying that the function is first going up and then it's going down. So the first derivative test is the following. If f has a local, let's just say it like this, actually without if. F has a local maximum at x naught if the derivative, or let's just say f prime x, changes its sign from plus to minus near x. So let's say when going from left to right. Okay, so so it's just like in this picture here. So we have at that point there, I have that the derivative changes its sign from positive to negative. So that's why I have a maximum there. So that means it's going from increasing to decreasing. Okay, so that's the idea. So if it goes from plus to minus, it's going to be a local maximum, and similarly you have a local minimum. So I'm going to just copy the whole thing and say that okay, now I'm going to change this thing and say that it has a local maximum. Instead of a maximum, I have a minimum now. F has a local minimum. At that point, if it changes the sign, now not from plus to minus, but it changes from minus to plus. Okay, so it goes from negative to positive. So so again, so when you have a local maximum, then you go from plus to minus, and if you have a local minimum, you go from minus to plus. Okay, so so are there any questions? We're going to do examples in a second, but are there any questions so far? Right? No, no questions. Okay, let's do one example. So let's do this example fx. So fx equals x squared. Okay, so let's find, I mean, we know already how this function looks like, what's what's the graph, right? But let's say we don't know, right? So how can we use this to find out what are the where is the function where it has a maximum or a minimum? So so here we find uh, local maxima and minimum. Okay, so what are the steps? First step, we find the derivative. Well, that's x squared prime, so that's 2x. Okay, second step, we find the critical points. So the critical points, so find critical points. So in this case, it means that solve this. Set the derivative equal to 0 and solve. Well, that's the same thing as saying that 2x, sorry, so 2x, right, is equal to 0. Well, that's the same thing as saying x is equal to 0. So your only critical point is x equals 0. Okay, good. So now I want to figure out whether this critical point is a local maximum or a local minimum. So what do I need to do for that? I need to, well, let's write the interval, draw the interval. Draw the number line with the intervals. Actually, let's just write instead of intervals with the critical points. Okay, so how does that look like? Where here, you just draw a line. In this case, you have just one critical point, so that's easy. And then you have two intervals, right? What does W mean? Oh, width. It means width. Draw the number line with the critical points. That means width. Okay, so we have now two intervals. So, and maybe I should write here and indicate the intervals of monotonicity. So that means the intervals in between the critical points. So there's two intervals, this one here and this one here. So there's two intervals. One is from negative infinity to 0. The other one is from 0 to plus infinity. 4. So peak points from each interval. So in this case, I'm going to pick a point. So let's take x. So peak x is x less than, so let's actually write it like this. From the interval x less than 0, peak x equals -1. And from x greater than 0, peak x equals 1. So then evaluate the derivative at that point. So then I have f prime at -1. -1 is the same -1 here. Well, that's equal to 2 times -1 because the function was given as 2x, right? The derivative was 2x. So 2 times -1. So I have it's -2, so it's less than 0. Okay, so it's negative. So I'm going to write here negative. Okay, what does that mean? That means my function is decreasing in this interval. It looks like that.
I have a question.
Yes.
What's that word at the end of step three?
What's the word? This one here.
No, step three.
Which- After three,
No, step three.
step three. So here, draw the number line. Draw the number line with the critical points.
The last word.
The last one. Oh, monotonicity. That means monotonicity. It means that where the function is monotone, and monotone means is increasing or decreasing.
Okay.
Intervals, I can write it differently. So I can write it and say of decrease or increase. That's the same thing.
Mm-hmm.
Okay, you can say the same.
All right. Thank you.
Mm-hmm. Yeah. So this one was with. Okay. So we found that the function is decreasing in this interval here, and then we're gonna pick uh, f prime 1, so that's going to be 2 times 1, so that's positive. So that means I have positive here, so that means my function is gonna increase here, right? So that means what do I have? I have that at this point here, I'll have the function is a local minimum. So because the function is decreasing and then increasing, so we have so these together. So so these things together imply that uh, f f has a local minimum at x equals 0. Okay? Any questions? So again, so what are the points? What are the steps here? So we first we find the derivative. Then we set the derivative equal to 0 and solve for that equation for x. Then we draw the number line and indicate the critical point. So in this case there was just one, okay? So then we want to figure out whether each of these interval is an interval of increase or decrease. So what do? We pick points from each of these intervals. From this interval, I just pick a point -1. You can take any other point, doesn't have to be -1. Just pick something for which it's easy to calculate the derivative. And so in this interval here, for x greater than 0, I picked x equals 1. And in both of these cases, I found that what the sign of the derivative is. Okay? After we do that, now we have that the derivative around the 0 goes from negative to positive. So that means at this point here, I have a local minimum. Okay? So let's do a similar example, a little more interesting one. So let's do this example here. So I have fx equals, let's do this 3 actually x to power 3 minus 3x. So and we want to find again local maxima minima of f. Okay, so again, I'm going to do the same steps I did before. So step 1, find the derivative. So the derivative here is going to be the derivative of x to power 3 minus 3x. So that's 3 times x squared minus 3, right? So I can factor the 3 out, so it's going to be x squared minus 1. Okay, so that's my derivative. 2, find critical points. What does that mean? That means set the derivative equal to 0. So I'm going to do 3 times x squared minus 1 equals to 0. So in this case, I can just, well, that's the same thing as saying that this part here is equal to 0. So it's going to be x squared minus 1 is equal to 0. But that's the same thing as saying that x, well, I can write it different ways. One way is that x squared is equal to 1. So that means x equals to 0 or so plus or minus 1. 1, negative 1, or x equals plus 1. Okay, so I have two solutions. I have solutions x equals negative 1 and then x equals 1. So those are my two solutions. So then I'm going to do the number line. So I'm going to draw the number line here. So, and I'm going to indicate the critical points. So the critical points here were negative 1 and 1. I don't have any points, any other points. And then how many intervals do I have? I have 3 intervals. I have this, I have that, and I have this one here. So the 3 intervals. And then I want to know again where the function is increasing or decreasing. Basically, I want to find out whether the derivative is positive or negative in each of these intervals. Okay, so that's 4. So we're going to pick 3 points. So let's start from the right. For x greater than 1, pick x equals to, let's say, 2, right? So if I do that, then I have to find what is the derivative at that point. Where is the derivative here? Here is the derivative, right? So so I'm going to plug 2 in the derivative. So I'm going to write 3 times, or actually let's just write it out. So f prime at 2 is equal to 3 times 2 squared minus 1. So that's 3 times 4 minus 1, which is positive, right? So 3 times 3, which is positive. So that means I am positive here, okay? So in this interval here, my function is increasing. Then similarly for x, now I'm going to choose now the second interval, this one here. So for x for x greater than negative 1 but smaller than 1, I'm gonna pick, well, I can just pick 0, right? So x equals 0. Then I have f prime at 0 is equal to 3 times 0 squared minus 1, which is 3 times negative 1, which is negative, right? It's negative 3. So that means in here I have negative. So the function is going to be decreasing in the interval from negative 1 to 1. And then I have for x less than negative 1, I'm going to pick x equals to -2. Again, I can choose any other number. It's just convenient to do -2. Then I'm going to do f prime of -2 is equal to 3 times -2 squared minus 1, right? So look here on the top. That's my formula for the derivative. So I'm going to plug instead of x -2. So I'm going to get 3 times -2 squared negative minus 1. So, and that of course is what? 3 times 4 minus 1, which is positive again. Okay? So I have that this is positive here. Okay, so now we're in good shape. Now we can use that's step 5. So by first derivative test, we have, let's just say not we, but f has, well, I'm going to leave some space here at x equals -1, and f has something else here at x equals 1. Okay, so there is 2 critical points, this one here and this one here, and I'm going to figure out which one is a maximum, which one's a minimum. Well, here, okay, so let's do -1. Here, the function has a derivative that's positive here and negative here, so that means the function actually is increasing before -1 and decreasing after -1. So it kind of looks like this. It's increasing and then it's decreasing, right? So that means at -1 I have maximum. So here I can write a maximum. Right? Because it's increasing then decreasing. And at x equals 1, I have a similar situation. Now I have, it's going to be near 1, it's going to be decreasing, and then it's going to be increasing, right? So that means at that point here, I have a local minimum. So I can write that here, f has, actually I should have said here, local minimum has a local minimum, and here it has a local maximum at that point. Okay, so we found 2 points where it could have maximum minimum.
Hold up.
And
Pause the screen,
yes,
sir. Can you pause the screen?
what?
I'm not talking to you. Can you pause the screen?
Make it bigger?
No, could you pause for a second? I just want to take a photo, or can I just take a photo of the steps real quick?
Sure, which part do you want?
Are you wait? Are you done with it, or are you not done with it?
I'm done with it.
I want the entire thing. The entire thing.
Well, I'm gonna send you the notes, the whole thing anyway.
Okay.
Oh, sorry, our owner just told me that there was a mistake. There is a I told local minimum, but so at 1 I have a local minimum. I'm sorry.
Oh,
I
okay.
said local minimum, but I wrote local maximum. You're completely right. It's a minimum.
All right.
Okay. So again, just like last time, I'm gonna send you the both the lecture, the video, and the notes. Okay. So what we got again, we did all these steps, found the derivative, set it equal to 0, drew a line with the critical points, and then found these intervals of increase and decrease. And then using the first derivative test, we just said that because it's increasing, decreasing, we found which of these critical points are maxima, which are minima. Okay? Are there any questions? If there are no questions, I'm going to go to the next problem. I don't see any questions, so let me do, okay, so I'm going to do problem 7. Okay, so it's very similar here, so I'm going to do it a little fast. So here is my function. So I'm going to find the derivative, critical points, and maxima and minima of the function. I'm going to just write fx is equal to 3t to power 5 minus 20t to power 3 plus 20. So I'm going to take the derivative of this. That's going to be 3 times 5t to power 4 minus 20 times 3 times t to power 2 plus 0, because the derivative of 20 is 0. So that gives me 15 t to power 4 minus 60 times t squared. Okay? So now I can factor certain things out because I want to set this equal to 0 and solve. I want to factor things out. What's common here? Well, this 15 can be factored because 16 is divisible by 15, right? So I can write that this is equal to 15, and then what else? I can factor t squared out because there is t to power 4 here, so I can factor t squared from that.
Moving
So if
kind of
I do that, I'm going to get t squared. Yes?
moving kind of fast there, buddy.
Yeah. Okay, well, so there is t squared here, and there is t to power 4 here. So I can factor t squared out, right? So I'm gonna factor that out and just write out what I get. If I factor out 15t squared from that, then I'm left with just 2t. So it's going to be t squared, and then I have 60. Well, 60, if I factored 15 out, 60 is 4 times 15, so it's going to be t squared minus 4. It's just arithmetic. There is nothing complicated here. Just factor it out. So that's my derivative. So the next thing is critical points. So the critical point means that I take the derivative and set it equal to 0. So that's the same thing as saying 15t squared times t squared minus 4 is equal to 0. Well, 15 is not important, so I'm just going to write that is the same thing as saying t squared times t squared minus 4 is equal to 0. But that's the same thing as saying that either t squared is equal to 0 or t squared minus 4 is equal to 0. Well, what does that mean? Well, t squared equals 0, it means that t is equal to 0. And t squared equals minus 4 equals 0, it means that t squared is equal to 4. Well, that's just t equals 0 here. And then this is the same thing as saying that t is equal to what? Square of something equals to 4, so that means t is equal to plus or minus 2. Okay, so those are my roots. The roots or the critical points are t equals 0 and t equals plus and minus 2. So I have 3 roots. So now I'm actually going to draw the number line. So let's do that. So let's draw the number line and indicate the points. So the points are negative 2 and 2 and 0. So I have negative 2 here. I have 0 here, and then I have 2 here, and so I have how many intervals? I have this interval, this interval, this interval, and that interval. So I have these 4 intervals, and in each of those intervals I have to figure out whether the derivative is positive or negative. So let's look at the derivative. That's what we're going to use, right? Oops. So this is the derivative, okay? And we have to figure out whether the function, that function is positive and negative in all these intervals here, okay? Okay, so I'm going to pick points and do this step by step. So I have first interval. Again, I'm going to start from the right. So let's do it like this. So for x greater than 2, pick x equals to 3, okay? And then I have to plug that x into this yellow thing. So then I have f prime, is it capital F? Maybe capital F. F prime at 3 is equal to 15 times 3 squared times 3 squared minus 4. Okay? And just calculating it, you see that it's a positive number. So I'm going to put a plus here. Okay? So for x greater than 2, I picked x equals 3, and I found that the derivative is positive, so I put a plus here. Okay? I'm going to do the same thing for the other intervals. For 0 less than x less than 2, so that's this interval here, I pick x equals, let's say, 1. Then I have f prime at 1 is equal to 15 times 1 squared times 1 squared minus 4. Okay? And if you look at this, this is clearly a negative number, right? Because I have what? I have 15 times 1 times negative 3. So it's just negative number. So because it's negative, I'm going to put here a negative sign. Similarly, for this other interval, for the interval negative 2 to 0, I'm going to pick x equals negative 1 and find the derivative at that point. So that's going to be 15 times negative 1 squared times negative 1 squared minus 4. Okay? So let's see what this is. Well, this is 15 times. I have negative 1 squared, which is just 1. And again, I have negative 1 squared, which is 1 minus 4. So I have what? I have 15 times 1 times negative 3. So that's a negative number again. Okay? So now because it's negative, let's look where I pick the number from. It's from this interval here. So that's going to be a negative sign there as well. Okay? And similarly for the last one, for x less than negative 2, I'm going to pick x equals to, let's say, negative 3. So I have f prime of negative 3. That's what? 15 times negative 3 squared times negative 3 squared minus 4. So if you do the calculation, you'll see that it's 15 times 9 times 9 minus 4, which is positive. Okay, all the numbers here are positive, so the whole thing is positive. So again, where did I take this? Where did I get that? That's for x less than negative 2, right? So that's this interval here. So I'm going to write a positive sign there. Okay, so that's what I got. I got that the function, the derivative of the function, this is f prime. So the derivative of the function is positive, negative, negative, positive. So if I could kind of sketch how my function would look like, it would look like this. It would be increasing here, right? Then it would be decreasing there. Then it would be still decreasing there. And then starting from here, it would be increasing. Okay? So what does that mean for this point here? Well, that means I have a maximum there, so local maximum. Here I have a local minimum. And what do I have here? Here I have neither. Right? Because it doesn't look neither like a mountain top nor a valley. It's increasing all the time. So it's neither local maximum nor local minimum. So here, okay, so just if you have a function that's, it's possible to have a function. Let me draw the picture here, actually. The function kind of looks like this. Near zero, it looks kind of like this. It looks like this and like this. So it's decreasing and decreasing. So that means at that point, I have neither a maximum or nor minimum, right? It doesn't look like this and it doesn't look like that. So it's not a local maximum or minimum. It's a critical point, but not every critical point actually has to be a maximum or minimum. So what I got is from this only expression for discussion, I get that f has a local maximum at which point? At that point there, at x equals -2. And it has a local minimum at x equals 2. Right? So just like in the picture here. See, I have, so it looks like this. At this point here, it goes from positive to negative. So that means I have a local maximum. And at this point, it goes from negative to positive. So it has a minimum there. Okay. And
Wait,
at this point here,
I have a
yes.
question, real quick. So you got that local maximum and minimums. How did you get those?
So those were the critical points, right? So first I found the 3 critical points.
Yeah.
I took the derivative, I set it equal to 0, and I solve, and I got 3 numbers. This one here and this one here. So this is 0, and there is 2 of them here, plus or minus 2. And then again, so I drew the line, I indicated these 3 points, and in between are the intervals where my function is increasing or decreasing. So to find out what happens 1 point here, I have derivative here positive or negative. That's what I was doing here. I was picking points to find out whether in this interval here, so in this one here is saying that in this interval the function is increasing because at that point here the derivative is positive. Similarly, then here I pick a point in this interval, then in this interval, and then in this interval, and I find out where the function is increasing or decreasing.
Oh, okay, I understand.
Okay. Okay, so if everything's fine, then I'm going to do the next one. Let me see. Okay, so I'm gonna send these solutions to you so that you can look, and now I'm just gonna explain it because um, I don't really have. Yeah, well, this is very similar to the previous one. Let me just go over this, summarize this somehow. Okay. So again, the same kind of a problem. We have a function. We have to find the derivative, the critical points, and the local maxima and minima. Okay. So again, the steps are the same. We look at the derivative. We take the derivative of this expression here. So let me make it bigger so you can see. So we have 2x squared plus this plus that. You take the derivative, is just the power rule. And then if you simplify it a little bit, you're gonna get this. Okay, this expression here. It's just a derivative, you just find it. Okay, now next thing, after finding the derivative and simplifying, we have to find out what are the critical points, right? So the critical points, if you remember, were the points where the derivative is 0 or the derivative does not exist. Here, both of these things can happen. See, if you plug, this is my derivative. If you plug instead of x squared 0, then this does not exist. So I have to check this point here. So again, the critical points here are the points where the derivative is 0. Well, this fraction is 0 if the numerator is 0, right? So I take the numerator, set it equal to 0, and it turns out that means that x to power 3 is equal to 1000, so x has to be equal to 10, right? 10 to power 3 is 1000. Similarly, g prime x does not exist. That means the denominator has to be equal to 0. That means x has to be equal to 0. Okay? So then I have again the number line. I have two critical points in this case. I have 0 and 10, right? 0 and 10. And then I can pick numbers again, and it turns out that the function has derivative that's positive here, negative there. So that means this one here is a local minimum because the function is decreasing then increasing. And then here it doesn't have anything because it's decreasing and decreasing. So at that point I don't have a maximum or a minimum. Okay, so that's what it says. So at x equals 10, g has a local minimum, and at x equals 0, g has neither a local minimum nor a local maximum. Okay. So it was a little bit fast, but I mean, the idea is very similar. It's exactly the same as the previous problem. So there is nothing new here. The only difference is that how you have to work a little bit to simplify your answer for the derivative so you could actually do these things. Okay. Are there any questions? Okay, so I'm probably going to stop here. The rest of the problems are solved. So if you guys want to, I mean, since it's already past 1:30, I'm gonna stop soon, but I wanna finish and go over this last problem because it's a little different. And if you look at the morning's lecture, I covered problem 9 as well. So it's very similar. It's just a word problem, but the problem is very similar. So what I want to do is I want to do problem 10. If you don't have time, if you have a different class, you can leave now, but I'm going to do this and post it online later. Okay? Okay, so let me just read this problem. So what's this problem here? It says Let's erase this. So we have a function f that's given like this. Okay, it's a polynomial that's quadratic polynomial, so that means the graph is a parabola. So what do we have to determine? We have to, there's many parabolas. Among them we have to find the one which has these properties. It has a maximum at that point x equals 2, and the height of that maximum, so the maximum value is equal to 7, right? So it has to have a maximum at that point, and the value of the function at that point has to be 7. So if I drew the picture, it would have to look like this. Well, there's many parabolas, but this one has to look like this. The maximum here has to be equal to 2 at 2, x equals 2, and the height here, this much here, would have to be equal to 7. Okay, so for that we have to figure out, the problem is find the a and b, so this a and b, so that the graph looks exactly like this picture here, where I have the 2 here, the maximum is at 2, and the height here is equal exactly to 7. Okay, so how do we do this? Well, we just do what we did before. We have to find the critical points. So find the derivative. So here is the derivative, right? It's a quadratic function, so the derivative is very easy to find. It's just negative 2x plus a. Now a is a, yeah, we have to find a, but we still have this.
Professor, I'm
Yes?
sorry to stop you. For that last problem, I'm sorry for going back, but for that
Mm-hmm.
last problem, right? In the homework, it says like
Right.
for the local max and a local min, like it shouldn't only be one x value. Like it got to be like say -2 comma 0.
Oh,
Like
so
that's,
for
so how would you put it? Like and when I put the 0, so like so I had the same problem for one of the homeworks.
mm-hmm.
Right? And it says
So I didn't realize that's how they asked it in the homework. But if that's the case, all you have to do is also plug that value inside f and find out what it is. So let me do it on one example here. So for instance, let's do this one here. So
which one?
actually let's do this one here. Okay, so we found that f has a local maximum at x equals -2. So here I'm gonna write it. F has a local maximum at x equals 2. So I'm just going to plug 2 here. So instead I'm going to do f of 2. That's going to be 3 times 2 to power 5 minus 20 times 2 to power 3 plus 20, right? And then I solve what it is. So it's going to be 3 times 2 to power 5 is 32,
Uh-huh.
32, right?
You just plug it in. So after you find the local and max, well, the
Right,
local.
so then you can write, so you got this number, so 3 times 32 minus 20 times 8 plus 20, so you got some number, so your answer is going to be 2 and whatever this number is,
Yeah.
like a pair. So if
Uh,
they ask you as a pair, then you should do it like this.
oh, okay. All right. Thank you. I appreciate it.
So that's local max, local min, the same thing. Okay. Okay, so here we were at this problem here. Again, we want to find a and b. so that these things are satisfied. So I'm going to do, so here what we found is the critical point is uh, the place where the derivative is equal to 0. So our equation that we got is negative 2x plus a is equal to 0. So if we solve, we're going to get this. And if we solve for x, we're going to get this. Okay? So the x, the critical point of this parabola is at a over 2. Okay? And in fact, it's a maximum. It has to be a maximum because the parabola looks like this, right? So the parabola has only one critical point, right? It has only one place where it has a maximum or minimum. It's at that peak there. Why do I know that it's a peak and it's not the other way? That's because the leading coefficient is negative. So the leading coefficient negative means the branches go down, right? So we talked about this. Okay, so so that means the critical point is that, and that's a local maximum. But in the problem, it says that the local maximum is x equals 2. So that means this number a over 2 is equal to 2. Okay, so and if you solve for that, you're going to get that a is equal to 4. So a over 2 is equal to 2. So a is equal to 4. Okay, so that's one piece of information we used. That was the, so it says relative maximum is the same thing as saying local maximum. And then, so the value at that point is 7. So that means if I plug f at 2, it has to be 7, right? But if I plug that from the formula here, if I plug 2 here, right, into this expression, let's plug and see what do I get. I get negative 2 squared plus a times 2, and I found a was 4, so 4 times 2 plus b, and that has to be what? Has to be equal to 7. So if I solve for this, I'm going to get what? This is going to be negative 4 plus 8 plus b is equal to 7. So that means 4 plus b is equal to 7. So b is equal to 3. So that's my answer. So you have to have that a is equal to 4 and b is equal to 3. So I did that here as well. Okay. Was this too quick? Was it clear or not clear at all? Well, since there are no questions, I assume it was okay. So I'll stop here. Do you guys have any questions? Anything? Okay, so I'll see you next time. So have a good weekend. Okay, great. Yeah, so I'll send you the recordings later today.
Professor, did you grant the request for me so I could do the homework?
When did you send your request? I think I've granted all the requests, so if I think it should be, you can check and let me know. It doesn't show me anything that I haven't granted. It shows that there is 0 request. That means everything is granted.
So where do you go to see that it's like that you granted it? You know what I mean?
I can't really tell you what the student view is. I see what my view is a little different from what you see. So,
Like,
but
all of them
on
still
website, I think it would show you the deadline. Doesn't it show you the deadline?
No, all the deadlines are like the same deadlines from like when I missed it. You know what I mean?
Okay, let me stop recording and we can talk.
All right.
Okay.